Welcome. This is Don Atanasio at the GW Law School and the leader of the Sustainable Energy Initiative at GW Law School. It's my great pleasure this afternoon to welcome Dr. Ben Cross. He's going to be speaking on the paradigm shift needed for how energy is produced and utilized. Dr. Cross is a senior advisor and founder for NuSynergy Energy, LLC. He's also a professional fellow at Ohio University's Voinovich School of Leadership and Public Service. As a senior advisor to DOE, he was also involved in defining the energy park concept for revitalizing DOE sites. With that, I'm going to refer you for the list of his additional accomplishments, which would otherwise take up all of his speaking time, to the bio, which is online. We will be putting that into the chat. And I'll remind you that if you have questions, you may put them into the Q&A chat, the Q&A function on your website. And then in addition, Dr. Cross will be available at 2 p.m. to continue any discussions. So with that, Dr. Cross, please.
Oh, thank you so much, Don. I greatly appreciate you sort of being persistent and getting me on board with this particular conference. I've learned a lot from it, like I told you earlier, and I'm happy to share. I got to do a quick shout out to Gene Carpenter, who obviously he must have always been listening to me when we used to meet for dinner a few times. Because I know he referred you, Donna, to me. Anyway, let's go on to my presentation here. The topics I want to talk about is why a paradigm shift is needed. And I think you've heard some of those reasons today. The critical success factor, if you want to change to another paradigm, you want to know where you're headed. What's going to cause you to have success? And then I'm just going to throw out a few reminders to people, and I want to particularly throw out a few reminders about nuclear. And then I'm going to propose what a paradigm shift looks like. And I'm going to give you an example of the project I'm working with through Ohio University and give you an example of one. And I think many of you probably have seen these charts before. They're a little bit on the busy side, but I wanted to point out to you in the upper, and like I said, I told Don earlier, I like to normally make these presentations where I have it animated. I took out the animation so we don't have as many technical problems moving the slides forward. But I want you to look in the upper right-hand corner where I have wasted heat. 67.2% of our heat goes to waste. That is the real key reason I see we need a paradigm shift. As you see, a lot of that comes from electricity, and the other side comes from mobile, from transportation down the lower right-hand corner. I circled that one as well, because it's going to be pretty hard to capture any kind of waste heat from transportation. Even though if you're on ships or trains, there's some other options, and you can be creative with vehicles probably to capture some of that heat and make it useful to you. But now you look at electricity, more than two-thirds of the energy goes to waste. And that's something we need to take a look at. One of my friends, Mike Zimmer, who's also executive resident at Ohio University, he calls the United States the Saudi Arabia of waste heat. Because with our individualistic mentality that we have, we want to do our own things our own way and really don't care what the other person does. We're going to go ahead and do what we want to do. And so we end up wasting a whole lot of things. As most people know, we're a throwaway society as well. But then I want you to look at that lower left-hand corner. That's 84% of the energy right there that what people see as mostly fossil energy, but also the biomass. But I like to point out that all emits CO2. And that's 84% of our energy. That used to be about 87%. It's now 84%, because now we do have some additional renewables that's come in to help reduce the amount of energy that we use that emit CO2. And I've circled the ones up there that are, everything sort of above the natural gas is obviously those are all renewable except nuclear. Of course, some people could argue that nuclear is also considered renewable. I also consider it sustainable, and and I'll sort of give you a reason why later. But nuclear only provides roughly 9% of our total energy. But note also, this mainly just goes to electricity. All these basically generate just electricity. Now, geothermal and nuclear, they actually can generate some heat, and you see where geothermal also puts off some heat. But I always would like to advise people, look at these charts every now and then and look them in detail. They can make your eyes sort of run together a little bit, but this shows you really sort of gives you a realistic picture of what energy is being used and consumed in the United States. Now I want to talk about those critical success factors. You're going to make a paradigm shift. What you need to know what's going to be successful. Well, I think this whole meeting has been a lot about integrating about diversity, talked about diversity. And I tell people everything you do, it's critical that you integrate diversity. I don't care what business you run or what operation you do. The people who integrate diversity the best are the winners. Just look at Bill Gates or Steve Jobs. That's just in the high tech areas of information. But if you go to any operation that's got to be done, those who can actually integrate diversity the best are the winners, are the most successful. Let's just use the word successful. And then I say second critical success factor is what I call IQ. And that's the iteration of integration and innovation. That means you integrate for what you already have. Take what exists, what you have, get it integrated, get it working together, and being efficient with each other. And then second is you need to innovate for what you don't have. That's where the R&D comes in. That's where the pilot plants come in. That's where the demonstrations come in. And then you want to integrate that innovation in. And then the last word again is iterate. Just keep repeating that over and over and over. That's what we got to do to be able to keep bringing ourselves more successful. As I was beating my head when I worked at Savannah River National Lab, continuous improvement. This is all about continuous improvement. The other one I like to steal from NASCAR, and that is co-opetition versus competition. And a lot of things in NASCAR, people have multiple teams, and they have where their teams have multiple cars, and they can work together, and they can learn a whole lot more when multiple teams are working together than they can if they had just one car. And I tell people we need all the above working together. We don't need them fighting each other, putting each other down. We need all of them to meet our energy needs as we move forward on a global basis. Then these reminders I want to tell everybody, these are sometimes what you call obvious, but I like to tell people if it's not integrated, it cannot be optimized. It's not going to optimize itself on its own. It's not going to be optimized. You have to first integrate it together. And then Einstein was giving for the next one here, giving credit for this one. He says, insanity is doing the same thing, expecting different results. I just want to add a little bit clarity to that. That's when nothing else is changing. But as a person who also has been working out for over 50 years, and I like to do that every day, and I got up this morning at 4:30 and worked out, but it's insanity doing the same thing and expecting the same results when everything else is changing. My body is changing. Other things are changing. I cannot expect to get the same results by doing the same thing. We have a whole country littered with companies that have tried to do the same thing and run out of business. Just ask Eastman Kodak or Polaroid. They will tell you they sort of ran out of business, or Blockbuster. You name some of these businesses, they run out. And the other thing I want, since this is a nuclear meeting focus, that nuclear reactors, let's think about basic what they produce. They produce neutrons. That's what fission does, make neutrons, and they make heat. When they make the neutrons get mad at each other, they sort of get hot and yell at each other, and they create heat. And lastly here, I want to make sure that someone knows as well that we recognize that the universe runs on nuclear energy. There's 600 million tons of hydrogen being burned every second at the sun, which is the closest star to our Earth. We're the third rock from the sun. But it's all that heat that we get that we're worried about coming here that's going to heat up this Earth. If that sun is not producing that energy, we're not going to heat up. In fact, over a period of time, we may heat up here temporarily, but over the long term, that sun is going to die down in power and we're going to cool off. So if you look at a real long-term look, the universe is powered by nuclear. If the universe is powered by nuclear, why should we be doing anything different? And so what should that paradigm be? And I use the word mainly just to give myself a caveat, but I don't want to be too dogmatic about it, but I think it should be the comprehensive synergistic integration of energy systems, both on the supply side and on the demand side. I want to just stop right there a second. That means we want the left hand knowing what the right hand is doing. The people who need to utilize energy, and we need the supply side, they need to match up. Right now, we have a lot of ways the people on the supply side are off doing their thing and they want to sell you something, and the people on the demand side are doing what they want to go do, and there's virtually little communication between the two. As we know, as smart systems are coming into play, that is changing rapidly. So we know that now more and more and more the supply side and demand side can work closer together. But then I say that besides just having that done, you need to be closely coupled with closed loop manufacturing. And that's where you utilize circular energy, circular economy concepts and technologies. And I say you're doing that to achieve sustainability with minimal environmental impact. And DOE has this graphic that they put out, and you can see that they have sort of different versions of it as well. But this is really where they're producing basically the two energy carriers. Again, as most people know, electricity is not a form of energy. It's not an energy resource. It's a carrier of energy. And same is true of hydrogen, which is a molecule. And that really shows the two things working together. This is DOE's attempt about bringing together what to do with electricity and with hydrogen. And you see all these different industries that are on the side as well. And so let me go ahead now just to tell you a little bit about closed loop manufacturing, because that's sort of key to this. That's a little different. That's adding on, because I'm taking some of those things on the right side and bringing them even closer together. Closed loop manufacturing, which a lot of technical people like to call industrial symbiosis. Typically today, we have what's a very linear approach. We bring in resources, typically natural resources, we make a product, and then we have waste, and we have byproducts. If we want to move more towards a circular economy, which is where we need to head, recycle materials, we need to be able to take that waste product, add some other new materials as well, make a product, and then that waste, the byproduct that comes out of it, feeds another factory that I say really needs to be co-located to be able to do that. Because if you have transportation of materials between one place, the more you have to move it, that's just like overhead cost. That's money that's being spent that you not have any value added being added to it. Now, the project I've been working on in Ohio, that's why you see down here about the Ports site, that's Ports Future. We talk about want to transform that facility from to an integrated energy system closed loop manufacturing complex. So this is just sort of a simple block diagram. This block diagram is really made for the local community just to see what you see across the bottom here, what some of the products that you would make. Obviously, from the power side, and if you're located in Piketon, Ohio, if you're located at that facility, you're co-located with the largest natural gas reserve in the world. So you start off with the natural gas. You got a lot of woody biomass in the area. You got a lot of agricultural grasses and crops could be grown as well. You got large cities that's not too far away. It's got a lot of municipal solid waste. And we show nuclear fuel as the future, because we're talking about you want to get started with what you have and take those heat sources, and those heat sources combined in with renewables like solar and wind to make electricity. Because again, they strictly basically make electricity. As we know, there is some solar that does heat out in the West, but for most purposes, solar goes to nothing but making electricity. And then we show making hydrogen, starting off with natural gas, steam methane reforming, but also doing carbon capture and using the carbon, the CO2 for a bunch of different uses, but then taking that hydrogen and using it for multiple uses as well, where these facilities is making these intermediates or final products would be co-located together at the Portsmouth site. We like to affectionately call it just ports. But to really show addressing that issue that we talked about before, which is really the waste heat, what we envision this particular complex addressing that. Our goal is to utilize the heat at every temperature level. And here's where for the process heat, this is what we call thermal management for the technical people. But co-location is key at thermal efficiency. When you have something that's hot, like your stove, put your hand over a stove, you move your hand out just a little bit, it drops off pretty fast. You can move electricity, that energy carrier, pretty easily. Hydrogen, you can move fairly easy as well, but it's going to be a little bit difficult in the early years. And when you try to get a hydrogen pipeline network in place, I even say if you're going to go with hydrogen, you're going to need to co-locate initially, because the best place to use hydrogen is where you make it. The best time to use it is when you make it. But back and focusing here on this thermal heat of use, when you see the port site in the mirror, that's roughly a 1,200 acre site. That's where we see the high temperature, high hazard, high security, high dollar investment facilities, like making the electricity, making the hydrogen, maybe making ammonia, making methanol, a refinery. When I talk about a refinery in the generic sense, it could be doing petroleum, biomass, any carbon feedstock, like even municipal solid waste. Metal extraction and treatment, you do that with the high temperatures. This is where we're talking temperatures probably close to 1,000 degrees C would be ideal. And some reactors we know aren't not capable of that yet. But however, from here you look at, as you sort of got concentric circles going out, you have various products that's being done as you go as you get to lower temperatures. So you want the heat of one process feeds another. And this is just a different diagram of the same thing, just shown in a different way. So how you would cascade these systems together, or what we call daisy chain them together. How you'd have this process heat, however it's generated by the fuel source, either natural gas, maybe initially biomass, municipal solid waste, but ultimately nuclear needs to be one of the key factors in this particular facility to do this, or any kind of integrated energy system, closed loop manufacturing complex. And then down here at the low ends, there's all kinds of uses for low temperature heat that can be utilized. Like I'll just only point out really, for time wise, anaerobic digestion. We now dump our waste into landfills and put French drains in there and put a vacuum on them that suck out the methane so it doesn't go up into the atmosphere, so we can use it for other processes to use what we call renewable natural gas. Well, we really should be putting those in tanks and making renewable natural gas on purpose under perfect conditions. That's the same thing with the grow houses and the greenhouses. Grow houses now with LED lighting, you can grow food indoors. Anything you put in a salad, which I'm a salad fan, basically can be made indoors and grown. One thing that I learned in this process, the average tomato travels 1,800 miles. That's a lot of CO2 being put out just for that tomato. And don't think the tomato is being raised for flavor or for nutrition. It's being raised to be transported. So anyway, there's a lot of benefits with this. One of the key benefits is what I call really stewardship, but it's effective resource management. And for most people, that's cost savings. For most of us engineers, that means higher overall efficiency. We engineers, we're taught about overall efficiency to take place, especially thermal efficiency. But it also does when we recycle water and the materials, including the CO2, where we actually want to repurpose that CO2, not just to bury it, not just to let it go into the atmosphere, but to actually utilize the CO2 to turn into other value-added products. That means better utilization of capital equipment and lower operating expenses. When you're co-located at a place like the Portsmouth site, you got a heavy industrial infrastructure, and you got facilities and personnel that can actually be shared. You share those facilities. And then there's shared processes. Almost every industrial process, you got common support systems like chilled water and compressed air and emergency fire water systems and other emergency fire water systems and security systems. There's just a lot of duplication of effort between one facility and another. If those facilities are actually co-located, they can actually share in those types of shared processes and resources that are available to them. Also, of course, one of the key things we want to look at is the use of domestic renewable resources. You want to be able to utilize things that are local, and we want to reduce waste and emissions. We want to minimize, get down almost next to zero, if at all possible. And that closed loop manufacturing, the idea is to drive down to almost what we call net zero or zero emissions. Can you get there perfectly? No, but you need to move in that particular direction. Of course, this is all to promote sustainability, and I like to add on an industrial scale. We've got into our situation that we have, like even materials that are made that we need to recycle. We made them on an industrial scale. We need to deal with them on an industrial scale. It sure is nice to have our cutesy little programs in our cities that recollects and cycles materials, and they take it and do things with it. And most of it, I'll be honest with you, now we know really goes back into the landfill. But we need to start solving that problem on an industrial scale. It's nice to have these other programs or can help supplement those or needed, not to take those away. But we got to start working on solving our issues on an industrial scale. And one thing about these integrated systems is one of the key things you get is price stability and predictability. And this whole group is about investment. This meeting is about investable nuclear. The investment world hates uncertainty. And what we really need to do is drive for price stability and predictability. A lot of investors would rather have a stable price and a predictable price, because look at our price of fuel that goes up and down, natural gas goes up and down, and all over the place. We need to be able to have where we can provide fuel on a predictable basis. And if we have a facility making synthetic fuels and making it on a consistent basis as well, you can get price stability and predictability. And of course, like what's important to the Portsmouth site and to a bunch of other sites that I know people's mentioned here as well, like former coal-fired plants, you can transform brownfield sites. We don't need to go be disturbing new greenfield sites. We got plenty of brownfield sites that we need to repurpose those particular sites and transform them into the new energy economy. Now, the challenges that you have. Now, this has been brought up as well. Integration is great to talk about, but getting multiple organizations working together, just planning together, you first got to get the people to talk to each other before you ever get any systems be integrated. I think once you get the people, and now I'm really talking about the CEOs, the executives, the captains of industry. By the way, I know some people would say we need to have government, and we need to have government help support and provide incentives for this, but we need the captains of industries to recognize it's in their best interest that for them to be globally competitive, they need to be able to start working closer together if they're going to be successful in the future. And so you really got to get the people talking to each other. Once you turn that over to the engineers, us geeky engineers will just have a field day of integrating these together. Then we'll be trying to outdo each other, how neat we can pull and do this together, just as you see what Apple has done and what you see that Microsoft and many other companies are doing today. But the problem is you got a large capital investment. When I looked at the port side, I thought about $40 to $50 billion could be invested there in putting this complex into place. Well, I see now that Plant Vogtle is already costing over $30 billion. We don't need nuclear to cost that much. We need to bring that down, but but any kind of large facility like this is going to have a large capital cost. And then there's big security, and this is investment protection for the people who's invested their money in this and want to make sure they get their money back, paid back from it. It could be issues associated with the security of it. We can't forget there are always terrorists that maybe want to go after us, either from a cyber standpoint or physical security, when you have things that are co-located together of any kind of industrial complex, because I'm really just taking industrial complex. It requires unique sites like the Portsmouth site. There's a lot of different sites across the United States. We've already put in the infrastructure, like I said before, where there's power plants, chemical plants, other plants where they're already there. But these need to be physically large sites where large dollars. We used to say a mega project was over $3 billion. That's probably a small number anymore. It seems more into the 15 to 20 billion. Of course, talking like Plant Vogtle, we're talking $30 billion, I mentioned earlier. But these sites need to be near energy and other natural resources. This is one that makes the port site very unique, be close to the Marcellus and the Utica Shale. But also the key things here you have to have is flexibility and resiliency built in. That's a challenge to make that happen, because if these facilities are actually somewhat independent, they are dependent on each other. You want to make sure you design them in such a way so they can also operate independent if one needs to go down for maintenance or any other activities that takes place for whatever reason they need to shut down. You don't want to be able to stop everything because one piece goes down. So this is where you want things modular, what they call process intensification, which now people are looking much more at. These become very valuable when you do things in a more modular standpoint. And then, of course, this is the key to developing one of these facilities, really do it in a phased approach and incorporate new technology, as I mentioned before. You start off with what you have, and then you start adding. So in summary, the IESCLM is not a new concept or technology, but an integrated approach for applying technologies. This is where you actually take and put things together, a systems approach, what I call focus on comprehensive synergistic integration. And then the ILS-CLM provides an opportunity, I mentioned before, about optimized efficiency and effective resource management. Already mentioned about the circular economy concepts you want to do. You want to minimize cost and impact to the environment. And again, enhance that stability and predictability of the price. And lastly here, I want to just say it addresses the nexus of energy, water, climate, food, and waste on an industrial scale. Again, this is very important for people around the world who don't have this. And there's other countries of the world that's moving in this direction, and I hope the United States will follow suit. Thank you for listening.
Thank you, Dr. Cross. We are running a little over, so I'm going to ask our audience to skip over to the next webinar, and we will have it up very shortly to hear from Dr. Arndt. Ben, this was really fascinating. You're preaching to the choir here at the Sustainable Energy Initiative, and we love hearing from you. Thank you so much.
I hope I wasn't preaching too loud.